I think this proof is probably the easiest division proof we've done so far. So the proof, we went with the logic already. So we start every proof, right? Well, it's a for all proof. So we start it with the particular and arbitrary thing, right? So let A, B, and C be particular, actually, let's do arbitrary first. It sounds better. Be arbitrary, but particular integers. Now, the whole thing about proving an if-then statement, that to prove an if-then, I'll say, remember, to prove an if-then, just need to show that whenever the hypothesis is true, the conclusion will follow. So all I'm saying here is we don't care about when A divides B is false, because when A divides B is false, so this whole thing's vacuously true, so we're good anyway. We only need to concern ourselves with when A divides B is true. And so we're just going to say assume A divides B. And so we need to assume A divides B, and then from just this information, because these are arbitrary but particular integers, they're just integers. We know nothing about them. We don't know if they're even, if they're odd, if they're prime, if they're squares, whatever. All we know is A divides B. We need to use that information to show that A must divide B times C. All right. Well, then what's the first thing we do usually in all these division proofs, all these divides proofs? Like eventually, right, we're going to want to say, eventually we're going to want to prove that BC divides A. Or sorry, A divides BC. And so eventually we're going to want to say, like, consider BC. Note that BC equals, they want to put a bunch of stuff here to eventually get an A times something, and that'll prove what we want, right? But to get to that, what do we need to do?
Do we kind of start with the definition of divides and like
start with the definition? I think that's a great idea, right? Sometimes when we've been doing like higher level proofs, you'll keep divides like this, and you'll use some theorems that you proved about divides to help us there. But for these kind of low level things, it's kind of the only thing we can do at this point is just expand out what this means. So then, by definition of divides, there exists a K and Z such that B, or I'll say, yeah, AK equals B. What do you want to say? All right. Now that gives us something to grab onto, right? Now we just like divide. It's like, well, this is the truth value. But this gives us some numbers to play with, right? We know there's an integer K. Let's play with it. So then note BC. Well, now kind of like the only thing we have to do is substitute what we know for B. So we know B is AK. So BC equals AK times C by substitution. And now we're almost done. This just equals A times KC by associativity. And associativity, remember, says we can move parentheses. which we know is true with the real numbers and multiplication. So we're good there. And by the way, it has to be the same operation we're doing, right? So it is true that like, it is true that A times B times C is the same thing as A times BC. It's also true that A plus B plus C is the same thing as A plus B plus C. Totally fine. What's not true is you can't say that A plus B times C is the same thing as A plus B times C. This is not true. You might say, well, we just move the parentheses around, and associativity works with multiplication and addition, right? But it has to be like a homogeneous thing. Like all multiplications or all additions, you can move it around. Clearly here you can't do it because you need to use the distributive law, which is nice. Which I think we've done enough algebra in our lives where this is obvious. But for other things, like, you know, I've seen this mistake with like P's and Q's and ands and ors and stuff. But the point is, yes, that's what associativity means. But anyway, we're basically done, people. Case is an integer. Why is K times C an integer?
Closure under multiplication.
Closure and multiplication, right? K and C are both integers by definition. Integers are closure and multiplication. K, C is an integer. So we've written BC literally equals A times an integer, which is the exact thing, the exact definition for being, for A dividing BC. So what this means is, so the note K and C and Z by their respective definitions, K here, C here, and the integers are closed under addition. So K times C is in Z. Therefore, since K times C is in Z, BC, which equals A times KC, is divisible by A by definition of divides. Done. So saying BC is divisible by A is the same thing as saying that A divides BC, just kind of written out. Any questions? Good. I think this is pretty obvious. This is just saying that if A divides B times C, clearly, because just adding an extra thing on top of it, that's fine. Yeah. I won't spend any more time on that. Cool. Can I erase? Then I will. All right. I threw baseball yesterday for the first time in a while. My arm is killing me. I am too young for this. Okay. Here we go.